Well, I think we can start. Welcome back, everyone. Oh, hang on. We're starting a little early, aren't we? Give me a minute. There we go. Now we can start. So our goal today is to do more review topics, as many as we can. I actually only wanted to do one more review on this document up here. Since there's one test that's not going to be on the final exam, the one from section 12.3, we'll skip over that one if that's all right with folks and just focus on the other material. Does that sound all right? Okay, so we'll do one problem from here. Then we'll kind of skip around. I think we should do a probability topic, but I'll leave it up to the class to direct us. Which topics should we take a look at in this document down below, the other review problems? So let's go back to this section. We're now up to example number 4. And if we take a look at this, let's see here. Right where it says the sample mean is 2,752 miles, that indicates to us immediately our data are numerical. So let's say here, this is numerical data. And now that we know it's numerical data, we want to know what kind of procedure are we dealing with. There's nothing about level of confidence. It's asking for a test statistic. It's asking for hypotheses. So if we go to the top of the document, here's what we would be doing. Grab the information for numerical data. Oh, I scrolled up too far. Here we go. So for numerical data, if we're going to do a confidence interval, this is the information we'd be doing right here. But again, this is the one problem that's not on the final exam. So I'll post this set of formulas onto the notes, again, to help out the homework. And then we'll go to the next one, which I think is going to be a confidence interval, maybe. I think I'm forgetting which one we're at. So for example number 4, these are the key formulas we'd be using. And now let's go over to example number 5. So reading through this one, let's take a look here. It says the USA snapshot. I think that's just a way of saying short article in the USA paper, USA Today. Social media jeopardizing your job is the title in 2014. And it summarized data from a survey of 1,855 recruiters. So we've got a sample size at least. And human resource professionals. It says in the snapshot, 53% of the people surveyed had reconsidered a job candidate based on his or her social media profile. And that's kind of shocking, but it happens all the time. And we are going to assume that the sample is representative of the population of recruiters and human resource professionals in the United States, which are the people you probably talk to in order to be finding a brand new job. So right here from this statement, it says 53% of the people surveyed, we had some kind of outcome. That right there, that 53%, that's enough to tell us this is categorical data. There's only 2 outcomes. It's going to be where they reconsidered a job candidate. That's the success, even though it sounds bad. And the failure is where they weren't reconsidering that person based off their social media profile. So on this problem, let's say we have categorical data. Let's circle that to indicate it. And now that the 53% has been identified, it says 53% of people surveyed. They're talking about percentage relative to the sample of 1,855. And so that tells us the 53% there is actually p-hat. P-hat is 0.53. Well, that's the rundown of the problem so far. We know we have categorical data. Analyzing the problem, we're asking for a confidence interval. And so now let's go and grab those formulas one more time from up at the top and run through the problem. First, any questions at the moment? Okay, so for categorical data, but if you're doing a confidence interval, the actual formulas we'll need are, let's see here, these right here. If we were doing a hypothesis test, that's a problem we already solved on these notes. We'd be using that particular standard error. So over here, let's grab these and just throw them into context. And that just barely fits. There we go. Probably doesn't have to be that small. First thing we want to do if we're running through this confidence interval procedure is we need to say what P is that the value P hat is trying to estimate. So we know P hat is 0.53, but what's still unknown is what in the world is the population characteristic? We'll write it out as P this time. And the only reason we're using the symbol P is because our data is categorical. If it was numerical and we had averages and standard deviations, we'd have used mu instead, the population's mean. If you start off with P, then P is going to be, let me try again there, it'll be equal to the population proportion. Then, so good idea to pause right here. We need now to think about the original context. This is always the population proportion of successes for categorical data with two outcomes, but we now need to work backwards and say, what was a success? Well, P hat is the sample proportion of successes, so we can use this line. 53% of people surveyed had reconsidered a job candidate based on his or her social media profile, and this is representative of the population of recruiters and human resource professionals. So let's see here. People surveyed had reconsidered a job candidate based on his or her social media profile. I feel like this one's a pretty tricky parameter to nail down. Anyone have a version they'd like to share with the class? Yeah.
Recruiters and human resource professionals that reconsidered a job and was based on the social media profile.
Absolutely, I completely agree with that. So let's go with population proportion of recruiters and human resource professionals. And what do? They reconsidered a job candidate. Here it says 53% of those individuals did this, that reconsidered a job candidate based on his or her social media profile. That definitely kind of sounds vile. You're working for a big company and they're looking at your Facebook posts and deciding whether you're a right candidate based off that. But I guess it's 2023. This is sort of the reality these days. This was based off 2014, and it's probably only gotten worse ever since then. So we could say here in 2014 if we'd like, or we could just leave this job or this article here carry that context. So I think that's a great parameter to indicate here. Next, we need to see if the conditions are met, but we're doing a confidence interval this time, and so the way the conditions are met change a little bit. Let's first take a look at this statement. They said, assume the sample is representative of those human resource workers and job recruiters. So we at least know we have a representative sample. Let's say down below, the sample is representative of all job recruiters and human resource professionals. Okay, so we got that statement down. We have a representative sample. Next thing we have to check is the sample size large enough? I mean, it definitely looks like it, right? We have 1,855, but to get full credit on this, we have to run through the motions. And that's one thing that didn't get copied down here. Let's make a mention. The conditions for the sample size are conditions for sample size are, we need to show that the number of successes actually in the sample exceeds 10, but they never told us the exact sample proportion of successes. They just gave us a statistic, p hat. this is where you'd probably want to use this formula. Check that n times p hat is greater than or equal to 10, and n times 1 minus p hat is also greater than or equal to 10. So we have to convert to these formulas in this situation. Does that make sense to folks so far? Okay, so p hat is the sample proportion of successes. If the sample size is 1,855, we can now say there are n times p hat. Oh, forgot to put that in blue. Just hit it with the highlighter. Sample size n is 1,855. And this is multiplied by 0.53. Let's get that number, and that's going to be the number of successes actually in the sample. Let me just move some windows over just a bit. Okay, there we go. I think that'll fit a little bit better. So it's going to be 1,855 multiplied by 0.53. So there's our first value there. We're getting 983.15. Now that looks a little bit fishy, right? These are supposed to be whole numbers. The reason we're getting a little bit of excess of 15% of one whole person is because p hat itself looks like it was probably rounded to 2 decimal places. So we'll take this one and round to the nearest integer and say 983 successes. Let's actually first say 983 is greater than or equal to 10 successes, and then do it all over again. The next formula is going to be n times 1 minus p hat. And this is where I usually make the comment, you do have options on this second computation. You could just take the total sample size of 1,855, subtract 983, and that's your expected failures. But if you like the formula, here's how it would be. 1,855 multiplying 1 minus 0.53. So this will come out as, back to the calculator, 1,855 times 1 minus 0.53 gives us this quantity altogether. Let's round this one up to the nearest integer of 872, which is definitely in excess of 10 failures. Now is the moment to scroll down a little bit. So we have 983 successes, 872 failures in the sample. So now we can make an overall conclusion. What we needed to show was this part and this part. If any one of those is below 10, then our sample size is not large enough. But here, the sample size is pretty huge, so we're probably in good shape. We'll say the sample size is large enough, and the conditions are met. So we're ready to go then and run through the rest of the confidence interval procedure. Because it's categorical data, our standard error is a little bit more built up, but that's the one that we practice quite often so far in the course. Before we go through the rest of the process, any questions at the moment, folks? Yeah.
So two things. If we do we like option round it to a whole number, or is it okay to leave it as a decimal when we're doing successes and failures?
I would say it's okay to leave it as a decimal, but I'm glad you asked that question because there is a really interesting guidance about this. When we're doing the confidence interval, we're expecting an actual integer for the number of successes actually in the sample. But if you're doing this one as a hypothesis test, say like on, I think that was our example 2. If you do this as a if you do this as a hypothesis test, this stuff, we expect it to come out possibly as a decimal answer, depending on what the p hat or p naught value was. So usually in a hypothesis test, it's an integer, or excuse me, a decimal answer, and that's normal. It's almost expected. It's rare to get 1130 exactly. But if you're doing a confidence interval procedure like down below, we're definitely expecting an ordinary integer. But if you did leave it as the 983.15, that's not a serious issue on the exam. Does that answer your question about those?
Yeah, and then I was also,
Mhm.
I just wanted to make sure these are like predicted successes and failures, right? It's not like,
Well, these ones right here would be the actual successes and failures.
Okay.
So just for the sake of taking a look at that, note we said 983 successes, so go 983. Divide by a sample size of 1855. I think that's up here as well. That's not going to come out as p-hat because, again, they rounded that thing on us, but let's see how close it is. It would definitely round nicely to 53%. So even if we rounded to 2 decimal places, that would be our conclusion.
I think I just accidentally clicked this down, but there's a different, like, there's a one we're doing like hypothesis that we're using predictive failures.
Yes, for hypothesis testing, it's expected successes when the null is true, essentially. Yes, question? I would say the bigger giveaway is in part A, you're just doing the population characteristic. And then down below, they'll ask for the confidence interval right here. So that's the major giveaway for that one. And if it's a hypothesis test, you'll know that that's the scenario or the situation because they'll say right away in part A, after your parameter, state your alternative and null hypothesis. So now you're squarely in the realm of the hypothesis testing. If it doesn't say that in part A, you can pretty much safely assume it's probably a confidence interval. Exactly, yeah. Other questions so far, folks? Okay, well, we've got the conditions down. Next thing is the mathy part of the whole process, like we've mentioned before. It's asking for a standard error. But if you ever wrote p-hat anywhere on your paper, the standard error should really look like this. SE for standard error of p-hat. Because it's not a hypothesis test, we're not going to put p-naught here. We never even wrote down a null hypothesis to put in such a value. Instead, what we're actually putting in is the statistic itself, p-hat. It goes here, and then 1 minus p-hat goes in the same location, and divide by a sample size n. So that's our first standard error formula we encountered, but we grabbed a number of them along the way. So in this larger context, it's still a pretty tricky problem. Any questions so far, folks, on either the formula or why we selected this one? Okay, well, let's run through what's going to happen with this. P-hat, let me scroll just to remind myself, yes, is 0.53. I guess we see it here as well. So this will be the square root of 0.53 times 1 minus 0.53. Divide that whole result by sample size n. And the n is from here to here, 1855. So that's what it looks like, pre-calculated. As a 4-point question, this is 3.5 points automatically if it looks like this on paper. And even if you ran out of time and all you wrote down is a formula, I would still give credit for just the formula as well. That'd be 1 point out of 4, just for putting this down on paper. Well, next, let's go and calculate it out. And just in case you have a different favorite way of doing it, you could always do it like this. Work out the numerator, 0.53 times 1 minus 0.53. We get a value. We can then immediately just divide by 1855. So division 1855. Now we have a number with scientific notation. We have to square root it. What's interesting is if you square root a number between 0 and 1, it actually gets bigger. So hit second, the power 2 key for the root. Hit second, the negative sign for your prior answer. And this is the result square rooted. It's now become much bigger. To 4 decimal places, we have a 0.0116. So now that we have a standard error, we're practically done with this thing. The confidence interval, it's just a matter of how fast you can write almost at this stage. So 0.0116. That look all right to folks so far? Okay, now that we have that value, I'm not sure what I did to the document. Everything changed on us, but that's okay. We'll go with this new font, if that's what they want. So part D is asking us to determine the value of a critical number for a 90% confidence interval. Now, after chapter 12, that might give us a different kind of gut reaction, but the good news is for categorical data, our critical numbers relative to the most common levels of confidence are already predetermined. And I won't throw a curveball and ask for like 92% confidence when we're doing this kind of categorical data. So let's go and grab T star, or excuse me, Z star. We need to go to the notes. This is probably something you already have available from one of your exams. It's a good one to bring to the next exam. And we want to go to 9.3 to find that table. At 90% confidence, Z star is 1.645. So this part D right here is almost just a formality. It's a pretty quick one to get through. Any questions on that critical number? Yeah. No, I wouldn't do that. I feel like it'd be kind of awful because we've never done that as an actual problem in the lecture. I would have had to have done several of those to make it a fair exam question. Other questions so far? Yeah, absolutely. Gotcha. Thanks for asking that question. We go to the top of the notes. My notes have a weird problem. The actual font changed and it changed some of the digital ink. I'm not completely sure what happened here. I'm going to fix the notes after we're done with it today, so the formatting looks a little bit more normal. But at the very top here on example 1, here's where we're trying to go. Everything got kind of messed up. That is weird. Let me see if I can control Z this back real quick. Let's take a quick screenshot here. Sorry for the random issue that came up. Come on, control Z. There we go. I don't know what happened, but I clicked on something and it broke all the notes. That is really bizarre. Okay, now back up to the top. We know we're dealing with, oh, still not there. Here we go. So now we know we're dealing with categorical data for sure. And whenever we're dealing with categorical data, what we don't have is this null hypothesis right here. Since the null hypothesis is missing, we can't plug in a p-naught value inside the standard error. Instead, if it's a confidence interval, we go for the next best thing. We always put p-hat in that location. Does that make sense so far? Awesome. And this is kind of the normal thing to do. What's kind of remarkable, and this only happens for categorical data, is that if you change the null hypothesis here, then the standard error also changes. And the whole reason for that, to address maybe the meat of the question, is the central limit theorem for categorical data involved P right here. So if we're not doing a null hypothesis, if we're just doing a confidence interval, we estimate this P using p-hat. We just throw it in. So that's if it's a confidence interval. But if we do a hypothesis test, we do this right away. We say, assume H0, that P equals P0 is true. It's always our first step in dealing with a hypothesis test. Assume the null is really true. And again, this is exceptional. If the null is true, this thing turns into root. P becomes P0 itself. So we just throw it in. P0, 1 minus P0 over N. So that's where that weird formula comes from. But it requires a hypothesis test to use that specific format. Other questions about that so far? Okay, so think of this hypothesis test formula as definitely the bizarre one in the set. Let's go back to the notes. And let's see, how much did I lose here? Actually, not too much. Let me see if I can put in the standard error back. 0.001. Oh, and let me fix that as well. 0.0116, and then T star is 1.645. Let me know if I misremembered that. Does that look okay? Awesome. Now next, we're ready to figure out, oh geez, I did make one mistake. It's not T star, right? We are dealing with categorical data. That one is Z star. That's not a good mistake to make. It actually can affect our work. It's best practice to definitely use Z star if it's categorical data. So now for the 90% confidence interval, the full format will be the statistic p hat, then add and subtract away our critical number Z star, multiply that whole result next by the standard error of p hat. So this really is pretty fast, actually, once we get familiar with the process. We can look up p hat right here. P hat went to 0.53, so let's plug that in. 0.53. Then we'll add and subtract Z star, which is 1.645. And last standard error, 0.0116. All we need to do is crank this out, give a practical interpretation, and that's one problem down. Any questions at all so far, folks? Okay, so next thing to take a look at is we need the definition of the population proportion. So let's grab this thing here. That was some rough penmanship. I'll try to clean it up on our end answer down here. So let's get our values. I'll put P in the middle. And this is just my way of formatting it. If you like the intervals with a number, comma, upper number, that's completely fine as well. Now back to the calculator. We'll go 0.53 minus a 1.645 multiplied by a 0.0116. We've got it all in, so hit enter. And here's our value for the lower end. Let's see, we're going for 2 decimal places on this thing. So this will be a 0.51. So the true proportion is bigger than 0.51. This means we can say that there is a majority of such people, candidates or human resource professionals, job recruiters, who will deny a candidate. It's above 51% at 90% confidence. That is a little bit low, so you have to take that into account. Now that's going to be less than, hit second. Oh, that's the wrong strategy. Let me clear that out. Hit second and enter to pull that up. Plus an enter now gives us the upper value, 0.55 after rounding. So 0.55 will go here. Now all we need is our practical interpretation. This is the step where whatever you have here, I'll go by that. And even if there's a mistake, just stick with it. You won't get double dinged on points. That's pretty terrible for double jeopardy. So we'll say, to start out, look up this number first with 90% confidence. Next, we have to indicate the population characteristic, and I'll change proportion to percent, since it just makes more sense as a practical interpretation as percentages, but you can keep them as proportions if you prefer. We'll say, with 90% confidence, the population percentage of human resource professionals and what else? Job recruiters, I'll just say, and recruiters, that reconsidered a job candidate based on his or her social media profile. Finally, we can say is between 51% of them and 55%. That does sound bad, but we also have to imagine maybe something was just given to them and they happen to do that at several occasions. It might not be something they do routinely, but some jobs, especially if they're very, very sensitive to their public relations, they might do a deep dive into your social media. That's, again, a really kind of a creepy fact about this day and age we're living in. But we did it, folks. That's the end of that statistical problem. And the notes aren't completed. I will solve this problem here and put down the solutions if you want to come back to it. But this is the one that isn't really on the exam. Any questions at all, folks, before we go to a different review document? Okay, let me say this. And now on the Moodle website, we're going for this one next. Other review problems down here. Once it loads up. Okay, so this document is just a bunch of randomly sorted problems. There's lots of concepts all over the place, but I'd say we should try one with probability first, just to get a feel for that. Does that still sound right to folks for our next problem? Okay, let me see if we can find it. So let's see here. This is z-scores. This one is regression. This one looks like a probability problem. We can tell by events are defined right away, so we're getting into probability. Problem starts off by saying, funding for many schools comes from taxes based on assessed values of local properties. People's homes are assessed higher if they have extra features such as garages, swimming pools, all those kinds of great things. Assessment records in a certain school district indicates that 73% of homes have garages, 11% have swimming pools, and 2% have both swimming pools and garages. So somehow, some way, this is the real deal. This kind of information does expect funding for public schools. Kind of weird, right? But that's how our system works, somehow, some way. We have two events defined. G is going to be the event that a randomly selected home has a garage. Let's go with green on that one. S is going to be the event that a randomly selected home has a swimming pool. That makes sense. S for swimming pool. And first thing we'd like to do is construct the hypothetical 1000 table. But before we get too far, we should indicate our probabilities. Let's read through here. It says, once again, 73% of homes have garages. That's our first event, G. So let's write out probability of G is 0.73. Next, 11% of homes have swimming pools. So that's going to be our event S. Although that looks funny, we could have said probability of sample space. If S is indicated here, it takes a different role. So it's just an ordinary event. This came out as 11%, so 0.11. Finally, it says 2% have both swimming pools and garages. But this tells us this last one is a probability statement that goes in this way. Probability of S, the word and turns into an intersection symbol. And intersection is a great thought to make because in our table, the number coming from here is going to be where the events intersect as one cell. So S intersect G is at probability 0.02. So that's our initial analysis on the problem. This stuff right here is definitely partial credit already. And if you write out this stuff, it says a hypothetical 1000 table. So if I see this on the paper, this is definitely partial credit as well. You're telling me you know what a hypothetical 1000 table would look like. And the more we put in, the more credit we are going to get from this. 1000 comes here from the name 1000 hypothetical table. Next, let's start with the event G. I'll put this in the column. G goes here. And G with the funny symbol C goes in here. This is now read as G complement. And that means this is the event that the person does not have a garage. Same thing on the row, the very top row, go S, S complement. And now there is one key value. We multiply this probability by 1,000. 1,000 times probability S intersect G would come out at 20. We move the decimal place 3 spots to the right. And that 20 goes somewhere in this table. Anyone spot where it'll be? Yeah.
The upper left corner. Yeah.
Exactly. So this is where G and S intersect right in the table. And so this is where the count of 20 goes in. That's pretty much our key step. Next thing we'll do is go to the other events, multiply this one by 1,000. 1,000 times probability of G is 730 on this one. So that's where we're getting most of our counts. But that 730 goes here. This is the total number of garages we would have had from 1,000 homes being hypothetically selected. So 730 in that spot, then just rinse and repeat. Multiply this one by 1,000. 1,000 times probability of S is now 110. So go down in the column, 110 goes here for that total. And I did forget to write one thing. It's not like a thing I would take points off of, but it helps a lot. Let's call this total. So I put 100 in the column total for S, swimming pools. Oh, and I made a mistake when I did that, right? That should have been 110. Let me fix that figure. Always good to double check the numbers as you go. And up here is another total. Now for the rest of this, it just turns into a pretty rapid little number game. You might not use the calculator, but if you decide to, here's what I would do. In this cell here, take 110 minus 20. That's not too bad. Let's put in 90. And then just double check that your column does sum up to 110. Looks pretty good. In this cell, we would take 20 away from 730. So it becomes 710. Now, let's see, down below here, take 110 away from 1,000 so that the number here totals to 1,000. This would be 890. And let's use a calculator for this one. By this red dot, you need to take 890 minus 710. Now the count of 180 would go right here. And last one, take 730 away from 1,000. We will get 270. And if everything went according to plan, we should really have a hypothetical table. There's a lot of ways to check this. You could just tally this column, and this column, and show you get the totals, 110, 890, and 1,000. Let's try a slightly different check. I don't think we've ever showed this kind of check in class, but if you like a different option, it could go like this. Let me fix that. I'm going to undo the yellow highlighting, but let's focus on these numbers. If we really did this table correctly, all 4 of these numbers must tally to 1,000 exactly. So let's check it out. 20 plus 710 plus 90 plus 180 does indeed come out to 1,000. That doesn't mean we did it perfectly, but that's very good in numerical evidence. We're on the right track. Well, any questions, folks, on this critical part, just getting the table in? Okay, now that we have the table, the rest of the questions are not too bad. Everything is addressed somehow through this table above. Part B says, what is the probability? So we have a probability function to start. That a randomly selected home has a garage, so G goes in first, or a swimming pool, or both. Here, we'll use the union symbol. Probability of G, union S. Everything is going to be divided by 1,000 in this kind of probability computation. So now we just need to take everybody that had a garage It was those individuals. Everyone who has a swimming pool are those individuals. And really the only way to make a mistake is if you use that total plus that total, because that would have double counted the 20 right here. It's best to just take the individual counts, 20 plus 90 plus 710. So that's what I would grab for this question right here. Does that look right to folks so far? Okay, let's work this one out. You know, the numbers are usually not too bad for this. This will be 800 plus 20. So 820 divided by 1,000. That just scoots the decimal place 3 spots to the left to a 0.82. So that's it, folks. That's our complete probability on this one. Any questions at all on that first portion? Yeah.
I also have a question on the hypothetical values table. Are we
Sure.
having an actual just a BFL table, or are we having a table that has a different sample now?
It's probably going to be this one is what I'm going for. It'll be at 1,000 for sure.
Okay.
Other questions so far? Okay. Well, with that so far, let's try now this weird statement. They gave us a probability function, and so this is a pattern we've seen on prior exams and questions. If there's a probability function given, you also want the the practical interpretation. So let's work this one out. It says probability of G complement, not having a garage. Maybe the most important symbol here is that one. Intersection means we're grabbing data from one cell. Intersect, S complement, meaning not having a swimming pool. So now, because of the intersection symbol, we'll go to G complement and go to S complement. We have to be in both cells at once. The intersection is right here. Does that make sense to folks on finding that value? Okay, if we're happy with that, then we're pretty much done with this portion of the question. Take 180, divide by the table total of 1,000, and this turns into a 0.18. What we need next is a practical interpretation, but after doing all those inferential statistics problems, this shouldn't be too bad. We could start off by taking this. You might say that there's a probability of 0.18. That's an acceptable answer. But I think it's more practical for saying there is an 18% chance that, let's see here, let's use this language, a randomly selected home, that a randomly selected home. Next, we need to say what G complement is. If G is the event of having a garage, the complement is not having a garage. So we'll say randomly selected home does not have a garage. So we mentioned the probability as a percentage. We went inside and we just read out what G complement means in this problem using the context. Right here, we're just going to literally say and. That's always excellent. The intersection symbol is conflated with and the union symbol is conflated with or, but it's an inclusive or, so it includes or both outcomes at the same exact time. That was the 20, where both things happened at once. So here, if you see the intersection symbol, just use and. S complement, go to where S is. It's having a swimming pool, so we'll say and does not have a swimming pool. So that's our interpretation on that one. Does it make sense to folks on the end answer there? Awesome, glad to hear that. Back when we were doing these in chapter 5, I could tell it was definitely probably the toughest part of the course at that time for sure. But now that we've gone through it, it's really just another number game, another interpretation, and then we move on. Here's a tricky question though. Are the events G, S independent? I think this one is very tricky. So let's work this out really carefully next. Kind of glad that we got to this point on the notes. This is a question that I was thinking of asking on the real final exam. Independence and mutually exclusive. And we're running low on time, but I'll ask and answer this question when I post the full solutions to these notes. Are the events GS mutually exclusive? Explain. We might not get to that one, but I will post the full solutions to this entire document. We'll put it on the Moodle webpage, and I'll answer that additional question as well, since I think that one's probably going to be important as well. So let's first focus on independence and see where we end up. Here's how I would answer this question. First step, let's take and calculate the probability of G just right away. Well, we don't really need to calculate it. We could just cite it, right? It was given to us. Probability of G is 0.73. So this goes 0.73 to start. Now we need to compare that to the probability of G given S. So that one is our conditional probability. And sometimes it's a little bit tricky to calculate if we're a little bit out of practice. Like say, we are a couple months away from this topic. That strategy here is the moment it says given S, that is our entire data set. We don't care about anything else in the problem. So go to your table. That column is of vital importance. We're going to get rid of S complement. It's just here to distract us now. We don't even need the total to the right. All we care about is this now. Does that make sense to folks on the redacted strategy so far? Okay, that means we have a new table total. The denominator is 110. The moment we said given S occurred, we have to recall there's only 110 ways S can occur. 110 homes with actual swimming pools. But it's also wanting the probability of G. There are 20 such outcomes that occur for having a garage. So 20 would go right up in here. Now it's going to be 2/11ths, or 20 divided by 110. And this probability looks like a nice repeating decimal. Let's round it to just say 2 decimal places to compare with the other probability. Probability of G given S is 0.18. This is a really weird area. I don't know if there's any area just like this in actual United States of America, but as far as the statistics problem, it's going to work out for us. After we do this, we need to make a comparison, and we're about ready for conclusion. We just found that the probability of G is not equal to the probability of G given S. So the next thought we would want to have here is, what is the probability of G? It depends. The full-on probability of G is 0.73, but if you know that the person had a swimming pool, the probability of G will change, and it will change drastically down to a 0.18. So because of this not equals right here, our conclusion will go like this. The events G, S are dependent. In other words, what we showed is the probability of G will depend on whether we know S occurs or not in this problem. Any questions, folks, with independence? Yeah.
If that is not like that, then
Exactly, yes. So that last comment is, if it ever looks like this, if the probability of G, instead of not being equal, if it's dead on equal to the probability of G given S, then we would say S is irrelevant. It's independent of G. And so G comma S are independent. So dependence versus independence depends on if you have equality, that's independence. If it's unequal, then we have dependent events. And let's see if we can answer one last question. Oh dear, no, we can't. We ran out of time. But I was going to say for the last comment, for mutually exclusive, I would say no. The only way they're mutually exclusive is if there's a zero right in there. That would mean the probability of G and S is zero for mutually exclusive. But I'll write out that full solution and upload it into the notes. Well, any last questions, folks, before we call it a night? Okay, well, congratulations on getting through the course. I was thinking earlier, mentioned it to the class. This is week 15. We meet 4 times a week. So this is like class meeting number 60 officially, although we did cancel a couple here and there. I appreciate all your hard work. And if you do have additional questions, on the day of the final exam, I do intend to hold office hours. I'll be in my office, tab 268, 11 a.m. to 2 p.m. Don't hesitate to drop by. There might be multiple people in the office, but still drop by, poke your head in, and get your question answered. Any questions?
Yeah, what sign has this stuff? I honestly don't know how to start this problem.
Oh, this one's kind of tricky.
Okay.
What's going on here is your conference interval always goes like this. X bar plus or minus a T star times the standard error.
Okay.
But that means because of the plus or minus there, your sample mean is the direct center of these both intervals.
Okay.
And because it's exactly in the center, you could average this, take that plus that, divide by 2,
Okay.
and you're recovering X bar.
So for both, I would add all of them and then divide by 2, or
You actually would only have to do it once, but you could double check. If you average this one, you'll get X bar. If you average this one, you should get the same exact X bar.
oh, so I literally just add them on the. Okay.
Yeah, it's one of those weird concept type of questions. Awesome.
I didn't hear like the.
Say how.
When you say how the process.
Oh, the evaluation,
Yeah.
yeah.
Like, no, I suppose. Or how do I do
It is optional, but it does give it extra credit opportunity.
I just didn't know how to get there.
Gotcha. So the spot it's at is right here. Bunch of stuff is just hidden on this little weird
There's a little
tab.
tab. Okay,
Yeah, and it's that very first link.
okay, thank you.
Yep, you bet.
This is point 1 today, right?
Yeah, that's right.
Glorious.
And that's the last assignment, so congratulations.
Oh, beautiful.
I have.
6.1. Oh, it's interesting. It's just
If
a,
anybody can do it.
it's a lot of data to track.
Yeah. Yeah, I have one more question. because
Sure.
our sign is the definition. What formula would I do if it's the estimate and not like an actual?
Let's see.
I just said 16 and 64, so I'm like, so what would I use?
Your upper and lower panels.
Scores on the scale can range from 16 to 64. I think they're just trying to distract us on this. We can skip over that. The scores over 40 indicate higher levels of procrastination. 67-year students in a study. For the 67 second-year students, that looks like a sample size.
Okay.
The sample mean was 41. Standard deviation was 6.81. So yeah, I think all your numbers are going to come from the sample mean 41, standard deviation,
Okay.
and the sample size there.
Okay.
This is just part of the context of the problem.
So would I go to 12.2 notes to find the one?
Yeah, it's all in 12.2. You can also do one of these problems here. We did a conference interval. You can follow the process on that one too.
Thank you.
Yep, you bet. Awesome, thank you.
You're welcome.
And when he was his calculus class, he allowed us to do that for the entire week.